Hello, everybody. So I don't know if the introduction's heard. So my name is Christian Wolf. I am associate professor at the LIRIS Laboratory in Lyon and at INSA.Lyon. And it's my pleasure today to tell you a little bit about deep learning. Now, deep learning is something I could talk to about for a long time. And basically, also these slides are a small summary of my lecture of deep learning, which is 16 hours and not just 2 hours. I'll try to be as concise as I can be. So a little bit about myself. As I said, I am associate professor in INSA.Lyon, which is 100 kilometers from here. And we are a small group of people with my students working on deep learning. And our targeted applications are learning computer vision and robotics. So we have, for example, work, I need to figure out, here it is. I'll need to figure this out. Give me just 1 minute. So, yes, no. What did I do here? Okay. Okay, sorry, no. We got it. 20.0. So we're working on computer vision, for example, with a strong focus on humans, understanding humans. So gesture recognition here, robot interactions, pose estimation. This is an application for virtual reality. Where are the fingers of a human in order to find out how to hold a virtual object, for example. Then autonomous driving. This is actually work which has been done in collaboration with researchers here in Saint-Etienne. And we also work on physics, understanding physics, for example. So deep learning, in deep learning, what do we want to do? We want to take decisions, and deep learning is a form of machine learning. And while it is very difficult to actually distinguish deep learning from machine learning, I would like to give the point of view when we learn from data which is embedded in high dimensional spaces, like, for example, images. So we have here input images, so objects, people, scenes in robotics, for example, and we would like to take decisions. For example, on the right side, we would like to do classifications, so detect objects. What is this here? This is a cat. It's my cat, by the way. What is the age of this person here? Then we would like to do robotics, like take decisions here. This could be an observation by a robot. The robot has a navigation problem. Find me that and that person, where do I need to go, blah, blah, blah. So the input is a sequence of images, and the output are decisions on do I need to go left, right, forward, backward, etc. We can also have fine-grained motor control, for example. We would like to learn commands like motor control, a sequence of continuous motor controls, which help me to learn how to take this glass, for example, and put it somewhere. So these are mappings, mathematical mappings, which go from high dimensional spaces to decisions. We can even go the other way. So for example, here, the output can be a high dimensional space. So we would like to produce this image here from what? From the semantic descriptions. I would like to have an image of a blue parrot with a yellow belly sitting on a branch in a forest, and learn how to produce this from data. And then I would like to have control on this. Oh, this is a nice picture, but now I would like to have the feathers a little bit longer, the back a little bit longer, etc., etc. So I'd like to control my decisions. And these are very, very complex decision functions. So go from a set of pixels here to a class is already very, very complex, because this cat here can have an infinity of different appearances, forms, sizes, positions. It's articulated. And so if I view this as a mathematical problem, it goes from a very high dimensional input space to a decision space. And this function here needs to be very complex. So the space here from going here, going from pointer, going from here to here, I need to learn a functional mapping which distorts the space in a very, very highly nonlinear way. So this leads me to the 3 problems of machine learning. We would like to learn these functions from data. And so we have these three problems in machine learning. First, I need to find out what is the function, what is the mathematical form of this function I would like to learn. So is the complexity of the function enough? Can my model, the functional form, can it represent the thing I would like to do? Going back from here, it's easy to see that, for example, we cannot take a linear function from the cat to the class cat. It wouldn't be possible. This is not a linear problem, right? Well, it's a non-linear problem, but what kind of functional form do I need? The next thing is trainability, because I will learn, I will do machine learning, and you had a lecture on machine learning already. We need to train these models. We need to solve an optimization problem. And this optimization problem can be quite complex. And the last part is generalization. So even if I have solved this problem, expressivity, so I have a model, I can train this model, and this model has very low train error. The question is, does it generalize? So does it also provide good estimates, low error on unseen data? So these are the three problems we'll need to address. I will a little bit mostly work on this part here because I only have 2 hours, and I will a little bit focus on this, and at the end of the lecture we'll go into the direction of generalization. So I will a little bit talk about the deep learning toolbox, and deep learning is not exclusively but mostly oriented towards deep neural networks. So we'll talk a little bit about standard neural networks, and there are a couple of different types of neural networks. The first one will be what we call multi-layer perceptrons. I will introduce them in 1 minute. But there are other types. And how can I choose between these two types? So if I'm not a deep learning professional, I would like to look at this like a toolbox in mechanics and have my different keys. And what is the tool I need for my task? Well, the tool I need for my task depends on what I know about the task and the data. So depending on what I know here, I will choose one of these tools. If I don't know anything or not much, then I can choose these kind of models here, which I will introduce in 2 minutes. And mathematically speaking, you can apply these models to anything because they can approximate any function, but it's not always the best choice. And there are a couple of others I will introduce a little bit later. Convolutional neural networks. When do I use them? Well, when I know my data is, for example, translation invariant. I will come back to this later. This is mostly in images. Computer vision, when I learn something in images, convolutions are really, really important. Next thing is, what do I use when my data are time series, sequential, and I have the Markov property, which I will introduce? Well, then I can use recurrent networks, RNNs. If my data are structured, for example, in the form of a graph, the geometrical, structural, then I can use graph neural networks. And lastly, if my data comes in the form of a set, so an unordered set, I can use this self-attention transformer types models. And it turns out that these models also work very well on sequential data. So if you currently use Google Translate to translate sentences, for example, from French to English, then transformers will be used. So what we'll do now is we'll look at all these models and check out why do we need all of them, what are the differences, and I'll give you a very high level explanation with a couple of toy examples which explain why they're useful. So the first one will be the MLPS, called multi-layer perceptrons, and they are the most inspired by biological neurons. So when we talk about biological vision and learning, then we have neurons, biological neurons in our brain. There are billions of them and trillions of interconnections. And how do they work? Well, they are cells which have an output and an input. So information is coming from the input here. These inputs here receive information either from our sensors, so our eyes and ears, or from other neurons. All these inputs are combined somewhere, and an output is produced. And this combination is learned. So whenever you learn something, then these connections here are updated. And an artificial neural network in deep learning is nothing different. Can you just give me on the chat a brief feedback on how much, if you know anything about neural networks? How quick do I need to go with this? Do you have any ideas about artificial neural networks? No? Yes? Who knows something about neural networks? A bit? One person? Okay. I will continue the explanation. So what is a single neuron, or a single unit, as we call it in deep learning? It's nothing else as a linear combination of values. So we have here a vector. These are inputs. This could be, for example, different pixels of an image, for example. And the neuron produces one output, and this output is linear. So here, it's a linear combination using weights. So each of these connections here has a weight associated, and this weight is learned. When we randomly initialize it, then there is no knowledge, and there will be random predictions, and then during the learning phase, we'll update them. Now, one neuron can't do very much. One neuron can learn linear problems, and linear problems are easy problems. So we combine them. So we combine them into layers. So this first layer here has one neuron, two neuron, a couple of neurons. And the outputs of all these units are combined, and we have again units. And we can have arbitrary amounts of layers, and each layer can have arbitrary amounts of units. And the number of layers and units will determine the complexity of the mathematical function you can approximate. And there is a theorem, which is called the universal approximation theorem, which tells you that one hidden layer, so one input layer plus one hidden layer plus one output layer, is enough to approximate any mathematical function with a couple of mild assumptions. You just need a high number of units here if your function is complex, right? Normally I provide the proof for this, but we'll not have the time today. So what I'm saying is that as soon as your data can be presented in vectorial form, in an image, this means you just flatten all the pixels in one vector, then you can learn any function, anything you want. It's just that it might be a bit complex and you might need lots of data, but it's at least possible. The model can represent any meaningful function. So how do we learn this? Mostly by supervised learning. So how do we interpret this? For example, we would like to classify cats, dogs, motorcycles. This is my input image. I calculate a couple of units, and my output function here has 3 different units. One, for example, for cats, one for dogs, one for motorbikes. The highest value wins. So if the red unit is the highest one, it's classified as a motorbike. So how do I train this? How does my network learn? I'll provide the input data here. At the beginning, all these weights are random. So I randomly initialize them, no knowledge. We provide input data here. An output prediction is provided by just calculating this. This is called a forward pass. We calculate the output. This output at the first iteration will be completely random. We use supervised learning. So in supervised settings, we know the answer because somebody has annotated the images. So we know here we have the labels. We calculate the error and we minimize. So we're from gradient descent. So this means that we need to calculate the gradients. Gradients are what? The error here is a loss function. It's the difference between my actual prediction, what should be predicted, and what we calculate is here the derivative. The gradient is nothing else as a vector with the partial derivatives of this error here with respect to the network parameters. And we go one step in the direction of this vector. This means when my initial error is here, there's a difference between my finger and the pointer, so this is difficult for me. So this is my initial error, and this is the loss surface here. So this is the error. Each point here, each point on this surface corresponds to one neural network or one set of parameters. And what I want to do is I want to go down here to the place where my error is small. So this is called gradient descent. And this is how we train neural networks. So we do millions, billions, trillions of calculations. And each step, we calculate the error, we calculate the gradient, and we go one step into the direction of the minimum. The gradient, the stochastic gradient can get stuck in a local minimum here, but mostly that's not a big problem. And I will not focus on this today. So mostly we're not too much worried about that. I will show you a little bit how this works in practice. For this, I will go back to my PC and run, I will share my screen. So I don't know if you guys know TensorFlow breaker. Oh, is this not? I need to go back and switch over to WebEx. Here it is. So now you should. Actually, what I want is WebEx. This is not the screen I'm sharing here for some reason. Okay, here it is. So now you should see, this is a website which is called TensorFlow Playground. And what you see here is a neural network, okay? What will we do? I will create a custom neural network. And the first thing we'll do is we'll look at the data. Here you see data. My data is two-dimensional. Here you see one dimension, and here you see another dimension. And each point here, each point is one data point, right? So this data point has a very low x coordinate and a very low y coordinate. This point here has a very high x coordinate and a very low y coordinate. Actually, they're not called x and y, they're called x1 and x2, because in machine learning, we very often call all the entries x and all the outputs y. So these are different data points, and the colors you see are the classes, right? So we have a two-class problem, and I can choose the kind of distribution I want to learn. So that's a very easy data set, right? So all my orange points are here, all my blue points are here. And this is my neuron here. It has x1, x2 inputs. It has no hidden unit, and there is only one output unit. The output unit is basically a scalar value, a number which tells me whether it's orange and blue. So basically, if this is negative, then we'll consider it's orange. If it's positive, it's blue. And I can initialize this randomly. And here you see the output, the decisions. I can threshold this. So here you see the frontiers. I randomly initialize my neural network, and here you see the decision frontier, right? What we would like to do is that the border, the decision boundary, goes in this direction, right? And when I randomly initialize my model, well, the boundary is random. So what I want to do is I want to learn, and this big button here will make it learn. So I'll just set it to learn, and a couple of epochs. What is an epoch? An epoch is all the data once seen, right? I can random initialize it again, and I click on learn, and it immediately and quickly learns a nice decision boundary, right? So we learned to decide, okay? Looks quite nice. So let's go to a slightly more complicated problem. So what you see here, this is called the XOR function, right? Because if you take x1 and x2 as two random variables, logical variables, this is XOR. So either x1 is positive and x2 is negative, or they are the other way around, right? So we can do the same thing. I can just randomly initialize my model, and then I run it. And what happens is, well, nothing happens. Nothing happens. It doesn't learn. It doesn't learn anything. Do you have any idea why it doesn't learn anything? Does anybody on the chat can give me feedback why this problem is not solved here? I mean, the decision boundary goes through yellow and blue points, and we have no idea why it's not really learning. The real decision boundary should be something like this here and something like this, right? So it's not working. It doesn't know a good solution. Well, yeah, what does no mean? Yes, exactly, Florian, because there's only one hidden layer. What there is zero hidden layer. There's one output layer. There is no hidden layer, there is one output layer. So how does this neuron work? What is the mathematical function for this? The mathematical function for this is, I will now try to use my pen if I can. Yep. Or I am not allowed to annotate here. I don't know why. Okay, no big deal. What is the mathematical function here? The mathematical function is a linear function. Okay, here it works. Good. So I have x1 here is one input, x2 is another input, and this is my output, this is y. So the mathematical function is some value, let's call it a times x1, plus some value, let's call it b times x2, plus some other value, let's call it c, and the whole thing is assigned to y. So y equals to this. Okay, it's a linear function. So one weight here, plus an additional bias term. This is called the constant bias term. And these guys here are learned. Okay, this is what we learn. Well, the problem is this is a linear function. And this here is not a linear problem. Linear function can only learn a linear classification, a straight line. They can only represent the border by a straight line, nothing else. So how can I remove this here now? I don't know. Okay, I'll try to do my best, but I have no idea how to remove this. No. Ah, ok. C'est parce que ce Webex est pas... Je pense que j'utilise Webex pour dessiner et pas le... Ouais, il faut que je le fasse à la main. Ah, bravo. Okay, thank you. So, this is a linear function, and what we want is we want to have a curve here, and a curve needs to be represented by a nonlinear function. What we'll do is I'll just add, okay, I need my pointer here. I'm a little bit troubled here. How can I get my pointer back? Okay, here it is. So I add one layer, okay, and a couple of neurons. So what we have here now, x1 and x2 will first be processed by 3 other neurons, and these 3 other neurons will learn something, and the output of these guys will then be given to the output neuron. Okay, one hidden layer. So let's initialize it randomly, and let's learn. "400 times the data has been seen." Yeah, not perfect yet, not perfect yet. Let's add a little bit more expressivity to the data. Much better. Okay, so now we learn a really nice decision boundary. Good. So I told you that with a hidden layer, with a single hidden layer here, oh yeah, one thing else, what I wanted to show you is that you see here, these little images here are the outputs of this hidden unit here as an image with respect to the different x1 and x2 items. So this each unit here learns a straight line, right? Each hidden unit here returns a straight line, but when we combine them again, it's not a straight line anymore. So I told you that the problem is not linearly separable, and I told you that if you have a linear network, then you can't learn it, which is true, but it's also lied, because I can, with a single network with no hidden unit, make the problem linearly separable, right? I can just add one more value. So here in my input is the x coordinate and the y coordinate, well, the x1 coordinate and the x2 coordinate. I can also input the x1 times the x2 value. If I take the multiplication of the x and y, so x1 and x2 value, and I call this x1 times x2, I add this as an additional input, then my problem becomes linearly separable. And I'm done. Good. I'll stop here. Yeah, we can do lots of other things. So for example, if I, for example, add a couple of neurons more, then I can even learn quite complex functions. The spiral is a little bit more complex and takes 10 minutes to train, so I will not work on this. So I'll go back to my slides. So this was a small introduction, and as I said, this MLP here can, in principle, learn anything you want.
Le sharing, il est sur votre...
Ah. On enlève le sharing, j'ai cru que je laisse, mais...
Et ouais, mais en fait, ça...
Ok.
Je vais y arriver.
Ah, évidemment.
Ouais, parce que sinon, il n'est pas sur le bon écran.
Oui, désolé.
Ah non, mais pas de souci.
Bien que vous êtes là.
Ça remonte un petit peu à quelque chose.
I'm sorry, switching back and forth is not my strong point apparently. Je devrais aller. Merci. Thank you. So as I said, in principle, these MLPs here can represent any mathematical function. So in principle, I can do everything with it, but in practice, it's not really the best way to do. And we'll see an immediate example right now when I will introduce convolutions. So what's the problem? Let's imagine we would like to find monkeys in images. So my monkey is here, and I would like to train a model which detects monkeys. So a single output, and monkey is yes and no monkey is no, 0 and 1, negative, positive, whatever. So I'll take all these pixels here, and if my image is 400 by 400 pixels and 3 color channels, this gives me 480,000 values. So one input vector here with 480,000 values. Let's take a very small deep neural network with only 500 hidden units. So there is one connection for each combination of input value and unit. So we have 500 times 480,000 values. That's already 240 million trainable parameters. So remember that these are the parameters we need to find through learning. And if we have many parameters and not much data, that can be a problem. More than that, also the second the second layer introduces units. We have 3 outputs and 500 inputs, 3 outputs, because I would, for example, like to find monkeys, motorbikes, and bananas, something like that. Then we have 1,500 more units because 500 times 3. Now that's a lot of parameters. That's too many parameters. Now current vision models have a couple of dozen million parameters. So that's okay, but not in a single layer. Now we have 150 layers, and in all these layers combined, we have 20 million parameters. So having 240 million parameters in a single layer, that's just too much. We don't want that. But it's not the only problem. The most important problem is that what happens if my monkey here moves from the left image to the right image? Well, then the weights, if I go back here, these pixels here are somewhere here and are connected to some unit, and the pixels on the right side are on the right part here, and they're also connected. So if my network needs to find monkeys on the left side and monkeys on the right side, then it needs to learn the same things all over again. So all these parameters here, there are so many of them, because they are tied to positions in the image. And for each position, I need to learn the same decision function. So I need to learn the same decision functions over and over and over again. Also, we would like to have the same decisions on the left and on the right side. So what we want, in essence, is we would like to have what is called a shift invariant or translation invariant mathematical function. Mathematical function does not change when the input changes position, right? So on the upper side here, I have a translation invariant model. When I move something here around, the decision doesn't change. Whereas this here is not translation invariant. When I move things around, the output will change. This is not what I want. Okay. Now, as I can see, the MLPs are not translation invariant, which doesn't mean that they can't learn a translation invariant model. That's possible, but it needs to learn to be translation invariant. What we want to be is, we want to have a function which is always translation invariant. So it's hard-coded into its mathematical structure that it is translation invariant. Translation invariant turns out to be a little bit tricky. What is a little bit easier is translation equivariant. What's the difference? Translation invariance, as I said, output constant when input is subject to some form of algebraic transformation like a translation. Equivariance means that the mapping, so the mapping is the functional form from the input to output, it preserves the algebraic structure of the transformation. Okay, that's a funny word. It's a funny sentence. What does it mean? It means that when I apply something to the input, the output is subject to the same transformation. So when I shift my output to the right, my input to the right, the output shifts to the right. When I go down, it goes down here. So what I see here is a code I wrote last year. This is nothing else than a neural network, and this is the intermediate representation. So these are a couple of layers in my neural network, and these intermediate layers here, I just color-coded them. And as you can see here, my network layers here are translation equivariant. This means that when I have two vectors here, like two images, 4 and 4, and this the right one is shifted to the left one, if I put both of them through a neural network, to the same neural network, if this network is translation equivariant, both mappings can be right. So this mapping can be derived from this one by shifting the input in the same way, by shifting the mapping in the same way we shifted the input. Okay, this is called equivariance. Now, how can we get that? By using convolutions. But let's just imagine we don't have convolutions. I will come back to what convolutions are in case you don't know. But let's just imagine that we don't have convolutions and we would like to derive this mapping. These will be the only slides with a little bit mathematics. It's not hard mathematics, so don't worry. So let's say we would like to have something like classical multilayer perceptrons, and we would like them to be linear and shift equivariant. Why do we want them to be linear? Because the non-linearity in neural networks is obtained by taking linear operations and stacking them together. I didn't really talk about this a lot, but this is not so important. So what we'd like to have now is a linear layer, okay, which is also shift equivariant. And what we then want to do is to put this linear layer just somewhere here. So we would replace this initial thing here by the same linear layer, but we want it to be shift invariant. Okay, so I'll go back. So what we want is linearity. What is linearity? If this is my image here, if I take two images and I multiply them with a scalar and I apply my transform, then the transform decomposes here. So this is the classical linearity. I want it to be shift invariant, which means that if I take my image and I shift it, so this is the shift operator, I shifted m pixels up and n pixels to the right. It's the same thing than first applying the transform here and then shifting the transform. So this is shift equivariance, okay? And let's just also imagine that I have what is called the impulse response. So the physicians among you and image processors know what an impulse response is. It's just the response of my operator with respect to a Dirac impulse. Okay, so these here are requirements, and this is just something I always have. Okay, that's just a definition. So let's just say that my linear layer here, my phi function applied to an image, it's discrete. And so I decompose it as a sum over Diracs. Okay, so this P here, these are Diracs. Okay, and I decompose my image into a sum of Dirac impulses, which I can always do when my image is discrete, and I apply my phi function to this. Then I can use linearity and move this phi function inside. Okay, this uses linearity. Good. Then these are direct impulses at the specific positions. I can use, I can just say, I use shift invariance here, and I just say, this is the same thing as taking a direct impulse at 0 and shift it around. We can use linearity again, and now have my phi applied to 0. And this is just my impulse response. It's not really important that you follow closely. We'll come to a conclusion soon. So we replace this thing by my impulse response. And the rest here, what I'm doing here is pretty easy. So I'm just changing my notation. So instead of saying this is a shift operator, I change my notation and put this shifting into my coordinates. And I'm at convolutions. So that's the important step here. What did I do? Let's just go back one step. What did we do? We defined a linear operator, which is shift equivariant. And we found out that the only operator which is linear and shift equivariant is a convolution. And this is the reason why we put convolutions into deep neural networks. So for those of you who don't know what convolutions are operations on matrices like images. So you have an input image here, for example, and the convolution is an operator which takes a matrix like this one here. These are the parameters. It's the kernel, the parameters of my convolution, and the kernel here is moved centered on a pixel, and then I'll just perform a linear combination of these values multiplied with these values, and that's my output pixel, my output value. Then I shift my convolution operator. I do the same thing, and I get the next value. And here you immediately see why convolutions are shift invariant, because they apply the same operation independent of the positions in the image. So how does this work? Well, this is one of the major contributions of Univ.Lyon, the now French director of Facebook AI research. He introduced this kind of layers 20 years ago into neural networks. This is the reason why we call this guy here LearNet from Univ.Lyon. And the little difference that you see here is that the input image here is actually an image, whereas in the other MLP version, we took all the pixels of an image and we flattened it into a vector, into one-dimensional vector. In convolutional neural networks, all the inputs, they keep their spatial structure. They are two-dimensional, right? Two-dimensional. So the units here also, same thing. The units are organized in a spatial structure. So we'll take this convolutional kernel here, we move it around, and we convolve. Second layer, again, we convolve. Third layer, we convolve. At the end, we can have what is called a fully connected, a linear layer, like an MLP, which takes the decision. Okay? So this is a neural network which is fully, depending on the parameters, but depending on the variant, it can be fully translation equivariant. I'll just give an example for a convolution. So take this image of a cat. Here we have a repetitive structure here. When you take out this shingles here, right? This small window here, and you define it as a filter kernel. So these are the values of my filter kernel. And I perform a convolution, I convolve my image with this filter here. I'll get strong values exactly at positions where my shingles are. Okay? So convolutions can serve as a concept detector. Okay? It detects things. And the nice thing is, since you have them in multiple layers, the first convolutional layers will detect stuff in the input image and create an output channel image where you have detection of these concepts. The second convolutional layer will detect concepts in the first one. The third one will detect concepts in the second one. So when you stack these different convolutional layers, each layer increases complexity. So we go from low complexity signals, signals up to very semantic, what is called features here. Okay. If there are any questions on this part, I can answer them now. I also continue. Okay. So now what happens if, so going from MLPs to convolutions is basically something we do when our data has some spatial structure, for example, images, but it can also be temporal structure. I can do convolutions in over time only, okay? Something else I can do when I have time series, sequential data, is I can use what is called recurrent neural networks. So here, what happens is when I take MLPs, I have a single vector, okay? I can put the whole time series into a single MLP, but that's not really something I want to do, because this means that I have a really high dimensional vector here if my time series is very long. So what I can do is, if I have this time series, for example, some signals, some low-level signals, some videos can have, do have a time structure. Robots, for example, a trajectory is nothing else than a sequence of observations when the robot goes through the scene. And obviously also, it's not really strictly speaking time, but there's a sequential structure in language, of course. We can consider the sequential structure as being time. So how do I do that? Well, we can take neural networks which have input for different time steps t. So my x input here is now in time index, and it goes into neural network. A neural network produces an output, but the output also takes, the model takes as an input some hidden state from the last time step. So there is some kind of memory in here. In this model, there's some kind of memory, a vectorial memory. And this memory propagates over time and influences the decision. That's very important because we don't want to deal with these observations as being independent, right? They're not independent, they're dependent. I'll not go into much detail, but why do we use these recurrent networks? It's when we think that my data follows what is called the Markov property. Markov property basically says that my decision at some point t only depends on the observation at this point and the state at the last time step before. I don't need the full observation sequence to take the decision, just my state at the last time step, and that's it. If this property is satisfied, then my model can be an RNN. So how does this work in practice? Okay, I didn't want to provide the full equations. I'll try to be a little bit more concise. What do you see here? These are my inputs, xt. At each time step, I have an input. It's 3 values here, okay? And these guys are my outputs, y, okay? So I have a mapping from input t to output y, okay? And what happens is my input x is not directly mapped to the output, but my input here updates what is called a hidden state, okay? The hidden state is nothing else than my memory. That's the memory vector I will update over time. So my memory at time t is some transformation, some linear transformation of my state at time t-1. So this is the dynamics here. In physical terms, if you have a linear system, okay, if you have differentiable equations, then this would be the discretized linear system, and this is my linear dynamics, okay? So this is the update matrix for my dynamics, and this is the matrix here which translates my observation into the contribution for the time step. So how is my observation at one time step integrated into the dynamics? So this equation here, and I have some pointwise nonlinearity here, like sigmoid or hyperbolic tangent, or some element-wise nonlinearity. So this equation here is the update equation for my hidden state, and then at each time step, I'll take the hidden state, and my hidden state is some update here, sorry, some linear transformation followed by element-wise nonlinearity of my hidden state. So y depends on age, and age is updated through its past value and the contribution of the observation, okay? So this might sound a little bit tricky, so I prepared a toy example. Oh, it shifted a little bit around. So don't be too, well, it's a little bit simple. So let's say you live on a farm, okay? let's say I live on a farm, and on this farm I would like to do some surveillance because at some point a wolf can arrive here. But the wolf can also be threatened by the farmer. So when the farmer is there, the wolf can come, no problem, the farmer takes care of it. But when the wolf arrives and the farmer is there, then we would like to sound the alarm. Okay? We would also like to sound the alarm if the farmer arrived, but the wolf arrived before him. So in two cases, if there is a wolf without the farmer, or if both are present, but the wolf arrived before the farmer because there was danger and the farmer needs to be alerted to search for dead chicken or something. In this case, we would like to have some output. Okay, so this is a sequential decision problem. In each time instant, I don't know why it's shifted here. In each time instant, we have input, and this input are observations. Let's say there's a camera. The camera looks at a specific place, and when some object like wolf or farmer arrives, it will send a vector describing this. Okay, this can be presented by the following recurrent neural network. And here what I do is I do not use machine learning. Okay, what I give you is an example with handcrafted parameters. This means that I provide my parameters in these matrices, I provide them myself. Obviously, in machine learning, these guys here, they will be learned by the network. Normally, I do not want to handcraft, never, okay? I want to learn this. I'll just show you how we can parameterize manually a neural network to take the right decision. So this is the same function before. Let's say my hidden state at HT is updated from the past state and integrates my observations, okay? Let's just, so this is my hidden state here. 4 values. How do I interpret these values? First value is 0 between 0 and 1 and tells me, did the wolf arrive or not? Second value, did the farmer arrive or not? Third value, how much time passed since the wolf arrived? Third one, how much time since the farmer arrived? I initialize these values all to 0. Everything is 0 at the beginning. Wolf not there, farmer not there, and these two we don't care because they're not there, right? So, now, what are these values here? This is my value here, my vector, which describes what person or object arrived, right? So if the wolf arrived, it has some kind of values. If the farmer arrived, some others. And this matrix here, which basically tell me, in this row vector, we'll put something which looks like a wolf. Here we put something which looks like a farmer. And when we do this multiplication, if a wolf arrives, this is translated to 1, 0, 0, 0. If a farmer arrives, it translates to 0, 1, 0, 0. So if I think about this equation here, if done correctly, will update. We'll put a 1 in here if a wolf arrives, and a 1 in here if a farmer arrives. So with this parametrization here, we just solved the problem of detecting the arrival of wolf or farmer and updating the memory matrix. Okay, it does not update the time here. Okay, well, this is the reason why we have 0 in here. So these guys handle the dynamics. So let's just imagine 1, 0, 0, 1, 0, 0 basically means that these guys are not changed, right? The dynamics does not update whether the wolf or the farmer arrived. In a sense, it will just keep it. Okay, if once the wolf arrived, it will keep arriving. It will keep staying here. Well, that's what we want. This thing here means update the time here by a combination of wolf arrived and the time, which basically adds 1 to this value here if the wolf is here, and will add nothing if the wolf is not here. That's exactly what we want, right? Once the wolf arrives, in subsequent steps, at each time step, this guy will be increased. Same for the farmer. Good. My hidden state here works, right? Once wolf or farmer arrive, we'll put ones here or here, and the time updates will be done. And then the second equation will just take the decision here. Y is a decision which will be positive, so higher than 0 if there is danger, and negative or 0 if there is no danger. And this is my handcrafted parameter vector, which tells me what? Well, the first 2 values calculate the difference between wolf arrived and farmer arrived. So if the wolf is here and the farmer not, it gives me 1. The second one, I'm just checking the chat, but Amaury is correct, is responding nicely. Thank you, Amaury. The second one calculates the difference between time since Wolf arrived and time since Farmer arrived. This is only meaningful if they're there. So if they're not there, they're zero anyway, so there's no contribution. And if these guys are both here, then this value here, this contribution is zero, and this contribution will be one if the Wolf arrived before the Farmer, and that's exactly what we want. Okay? So, good. Now, this was a very long example, but basically what I want to show you here is that these kind of models here can learn dynamics and sequential decision processes. Obviously, we don't work as I just did. Okay, this was just an example of how these models can be interpreted and how we can parameterize them. In reality, all these matrices here, they are not handcrafted by an engineer and expert. They're learned. They're learned through the same method as MLPs, gradient descent. We make a forward pass through the whole model here through the full sequence. We calculate some loss function, some error, and we update all the parameters. The parameters are here, these different values. We update them by calculating the gradients and adding the gradients to the precedent values. Good. Okay. Just checking the chat, but should be okay. Yes, what I didn't say is not, these are recurrent networks. They're a little bit simple. And we also see they're only linear here, right? Because we have a nonlinearity here, but basically they are linear models. In reality, what we do is we stack them. So basically, there's one of these equations here, and instead of directly calculating the output from the hidden state, this hidden state goes in a second layer hidden state. The second layer hidden state can go into a third layer hidden state, and the third one goes, for example, to the output. So we can stack sequential recurrent models like we can stack any layers. And also, just briefly mention it, I will have no time to explain this, and I don't know why this is so funny here on this computer. The equations are mixed up. But anyway, the real variant which is used are called LSTM, long short-term memory networks, which are a little bit more complicated. You have these gating functions. I will have no time for this. I'm just saying that the really used variant in academic and industry are called LSTMs, and we can talk about this later if you have questions, or you can look it up. Okay, I am on time. Sounds good. I can even spend as much time as I wanted on graphs and transformers. So what we dealt with now are arguably the three highly used models up to 2-3 years ago. Now graphs, graph networks are models which we use when we have highly structured data. So anything where you provide a prediction for a set of items, and these items are related to each other through, for example, neighborhood criteria, kinematic trees, for one example. So this, you see, this is looking like a human person. And why? Because, for example, when you do pose estimation, I can even go back all the way here to my input slides. So here, for example, this would be some kind of kinematic tree where the goal here is, for example, to decide what is the position. So that the neural network sees the input image here, and it decides on the 3D coordinates of the different joints of my fingers. And it outputs, so for each finger, it outputs 3 values. So if you have 25 finger phalanxes here, then I need 75 coordinates. Now, they're obviously not independent. You can't move your fingers in an arbitrary way, right? So the fingers are related to by the joints, etc., etc. So they create some kind of graph, and you can use this graph to impose constraints on your solution. And that's exactly what we do. I'll switch all the way back. That's exactly what we do when we use graph neural networks. I only talk about graph neural networks. There are also more general neural networks where you work on 3D surfaces and 3D meshes. I will not talk about this today. So strictly speaking, the recurrent neural networks are a form of graph neural networks in the sense that the sequence here can be a linear structure, right? Just a sequence. Images are arguably a form of graph neural networks where the graph structure is 2D, a 2D lattice, but we're most interested by these more general graph structures. So what is a graph? Oh my God, I'm sorry, my equations are a little bit messed up here. So a graph consists of a set of vertices, and they're also pixelized, I don't know why. A set of vertices and a set of edges. And so per se, a graph doesn't have any spatial or geometric structure. It only has topology, so a graph structure, and you can move the vertices around as you want, and you keep the graph, you can even calculate graph isometries. But in reality, we mostly work on attributed graph. We have some measurements associated either to only the vertices or to the edges or to both. They're called attributed graphs. So I will present this here through these vectors here. For example, this vector here is associated to these vertices. This can be, for example, appearance, for example, of some object in a scene. If your graph represents a visual scene with each node being, for example, a person or part of the person, etc. In the pose estimation example I gave before, this would be, for example, geometric information around the finger. So what do we want to do? We would like to take decisions on a graph. So there are a couple of things we would like to do. Is our input is a graph here, okay? So a set of nodes, a set of edges, a set of attributes for nodes or edges or both. And what we want to do is to take decisions. There can be either a decision taking for the whole graph, so classification. Your graph could be, for example, finding whether in a scene there is a presence of a certain kind of object. Or it can be a decision for each vertex, okay? I forgot to put an image in here, but let's imagine that your graph here is a LiDAR of an autonomous car. In autonomous cars, you can get 3D point clouds back, their graphs, and you would like to find out, is this point here in the scene, does it belong to a pedestrian, a car, a traffic sign? So you would like to take a decision per point. So you can have both, either per graph or per point. So what could we do? Well, I told you that we can solve everything with standard neural networks, MLPs. So can I do this? Can I solve this problem with an MLP? Of course I can. I'll just take all these vectors here, I concatenate them, I create a very, very long vector with only all these vectors in there, and I train a perceptron or a multi-layer perceptron or something on this data. This can be totally done. What's the problem? Why? Actually, I want to ask you the questions. Why don't we do that? It can be done. It's mathematically possible. It's simple to do. Why don't we do that? What would be the downside? Very similar to the downside why we don't use MLPs for sequential data, by the way. It's very similar reasoning. Nobody? Okay, if we do that, then what I don't get is the fact that, first of all, if my different graphs have a different size, okay, if my population of graphs is a variable size, so some graphs are small, some graphs are big, and I would like to be able to put all the different types of graphs into a network and take a decision, then this doesn't work, because an MLP, per definition, needs to have a single vector and each item has the same size. So that's the first thing, which doesn't work. Second thing is, all these vectors here correspond to a description of one of the nodes, right? This one corresponds to this node, this one to this node, and these vectors have different dimensions, right? So this dimension here corresponds to this dimension here. So the thing here is, this value is a descriptor. It could be, for example, I don't know, if it's handcrafted, it could be a size or an angle or something. So this value is the same value than this one. It's just a descriptor for a different node. Same one here, the blue guy. The blue guy is some kind of descriptor, and this guy are the same one. They don't have the same value. Of course not. They have the same interpretation. They are just values for different nodes. If you mix all if you mix all these vectors in a full MLP, then your mathematical description is completely lost, right? The MLP has no clue that there is independence, conditional independence between these different subparts, and it needs to learn these associations from scratch. It doesn't have them. So we want to create a model where the model understands that, first of all, these vectors here are similar. They are different expressions of the same mathematical thing. And we would like also to input the relationship. So these two are neighbors. So what we want to do is something like, okay, it's called relational reasoning. Okay, so we have sets here. We'd like to have a function g, which takes all these x's. These x's, all these vectors we have, right? It takes all these vectors and it creates a function. And we would like to learn this function. And also, the sizes here should be variable. So for one sample, n goes up to 10. For the next one, it can go up to 30, etc. So these sizes are variable. So one mathematical function which has variable number of input vectors, and there are not so many of them. And the easiest one, it's called PointNet in a geometric context, is to learn first one function h for each independent x here, apply the same function over all the items, calculate the maximum, and then go forward with this maximum. It sounds a bit strange. I will give you a very, we'll again talk about wolves and farmers. I will give you an example for this. The second one is a little bit similar, but instead of just calculating an h which takes 1, it calculates an h function which takes pairs. So it takes all the different pairs of items, and it passes them through a function, and it sums them. Okay, this sounds really strange, I admit it, okay? It's hard to digest, why do we need this? But I'll just explain it in more detail, but let's just look at it from one perspective, which is, does it fulfill the constraints? It fulfills the constraints I just mentioned before, because first of all, the number of points here does not have an impact, because the maximum here can be calculated any number of points. So this is the first constraint. And the second one, similar values here, so that all the yellow points should be known to be together, all the blue points should be known to be together. Well, the same thing is because the same function here is applied, h is applied to all the different points. So this function can learn what does the yellow, the first scalar mean, what does the second dimension mean, what does the third dimension mean, etc. So this is really nice, but it has lots of limits. Before we talk about the limits, let's just look at it graphically. So we have our different input items, x1, x2. Okay, I just showed 2 of them. Each one is projected into a neural network, so one linear function plus non-linearity or something like that, which gives me a new vector. This vector here describes this vector. So it calculates what we call features. It transforms, it goes from one vector space to another vector space. It describes how this point is transformed. And I do this for all the different points. Here only have 2 of them. In reality, there might be lots of them. We currently apply this model on point clouds for cars, right? We can have millions of points on cars. We would like to learn aerodynamics on cars, for example. How do cars behave? We use this kind of models, okay? One transform from each point on the car, then we just max them over the full car. So the maximum operation here gives me a vector of the same dimension, of the same size as this one, and then a new neural network here, and this provides me the output. So that's the most important part. 2 different neural networks. The first one is applied point-wise, so each input point. We accumulate this over all points, and we have a second neural network, which is applied on the sum. So this is called PointNet. It's a model from 2017. It's really easy and strangely widely used and very powerful, also very easy. We can a little bit make it more complex by doing relational leasing. So basically the first model takes all the points independently. The second model introduced by Santo, etc., takes points per pairs. So it goes over all pairs of points. For example, in graphs, it could be neighbors linked by an edge. It takes the two vectors of both of these neighbors, puts them through a non-linearity. So some neural network here creates a new vector, same as before. The only difference is now it's two of them. We add them or max them, same, adding max doesn't change much. And then a new neural network which takes a decision. Okay. So let's check a toy example again, and let's again talk about wolves and farmers. And I now also add sheep and cabbage. Okay. So this is actually quite a well-known problem. So we have lots of items. The wolf can eat the sheep. So the problem here is we want to find out, does somebody get eaten, right? So if the wolf and the sheep, it's not a sheep, it's a goat, sorry. The wolf and the goat are on the scene. If they're both on the scene, well, the goat gets eaten. Unless the farmer is also present. If the farmer is present, he prevents the wolf from eating the goat. So it's not getting eaten, right? If the wolf is present with the cabbage, no problem. The wolf is not vegetarian, will not eat the cabbage. But if the goat is present with the cabbage, then it will be eaten unless, again, the farmer is present. He will prevent this. Now, for those of you who are interested, this is, of course, a well-known riddle where you have a boat. You need to try and go over a river, and there are only two places on the boat, and you need to put the goat, the farmer, the cabbage, and the wolf over the river, and nobody should get eaten. But anyway, this is a smaller, simplified problem. And what we want to do is we want to be able to treat all these graphs here, right? So also more elaborated graphs. There could be like 15 nodes. You could have 15 nodes, and each node can either be a wolf, a cabbage, a farmer, or a goat, or even something else, right? And they could be arbitrarily connected. And you want to have a neural network, which is capable of working with any number of input items and output the correct decision. Of course, this can be solved by programming, right? I mean, this is a logical problem. You just have a couple of logical rules to follow, and that's it. So if you have this problem here to solve, and if this is your industrial problem, then you need to look, you need to check your life choices, right? This is really a toy problem. So never, ever will we use this for machine learning. But it's a toy problem. What we want is we want to be able to have a neural network who can learn these decisions, right? So let's imagine I have a data set where you have all these input graphs. You don't know the rules. You have no idea what these rules are. And the only output you have is yes or no, somebody gets eaten. And you want to learn this decision. Now, again, this is a toy problem. Real problems are much more complex. But let's just check how this works. So we have input vectors. Here, these vectors are some kind of descriptions of what we see. So each vector here describes an object, and obviously these objects can be wolves, cabbage, goats, and farmers. So the first neural network here will just learn some kind of object recognition, right? So if the visual descriptions of the four object types are quite different, then we can imagine that there is an object here, an object recognizer, which puts one in here if the thing is a wolf, and one in here if it's a cabbage, and one in here if it's a goat, and one in here if it's a farmer, and obviously only one of these guys will be one and not multiples, okay? So this is completely possible and also very easy to do, okay? So the first level of my point net model, of my graph network model, will just take this visual descriptions here and recognize these guys. Now, if I do this for all different nodes of my graph, for each one of my nodes, I have this representation. I'll just then apply max pooling. So I'll calculate the maximum of this thing here. And then I have, since the maximum will tell me if a wolf, for example, was present at least once, there will be a one in here. So this maximum operation, which can accumulate correctly the presence information of my scene. And then this network here just needs to learn some kind of mathematical logical function with an MLP. It's a nonlinear function which tells me exactly the rules I want. If there is a farmer in there, then it's no, nobody gets eaten. If the farmer is in there, then two cases need to be considered. wolf plus goat or goat plus cabbage, right? And that's done. So the network can learn that, okay? So the funny thing you can see here is that the dimensionality of this vector here needs to be appropriate, right? Since this maximum rule here is very easy, very simple, this will not do any logical calculation, there needs to be enough information in this vector here to have all logical combinations of data points, right? So if your problem is very complex, there are complex combinatorial situations in your graph, then you need what? You need a complex mathematical model here, a complex, lots of parameters here, but also lots of values here, right? If you have an arbitrarily complex function here, an arbitrarily complex function here, but only a couple of values here, your problem might not be solvable. So these are hyperparameters which you need to optimize when you train these graphical models. Let's go back to the other model. So as you can see here, now before we go back, remember we have 4 values here, right? Presence of wolf, presence of cabbage, presence of goat, presence of farmer, right? Good. Let's now go to the second model, which not takes individual items here, but takes them pairwise. So it takes all possible combinations of nodes, all xi, xj, passes them through this neural network. And here we can have these 3 values. Once more, I really want to insist that this is not the way how we do machine learning, right? These guys here, the interpretation of my vector here, it's normally not handcrafted. There's not somebody like me who tells you that this value here means this value means that. I'll just show you what the network can represent. In reality, all this is learned. The parameters here are learned, and the interpretation of your what is called embeddings, this is called an embedding, it's learned, right? This is just a crash course on representational power of certain types of neural networks. So going back to the second type of model, again, we have these pairs here. Then we can see we can survive with only 3 values. Before we had 4 values, remember? 4 values, 1, 2, 3, 4. Now in this version, we can survive with only 3 of them. The first one is the presence of the farmer. The second one is the presence of cabbage and goat. And the third one is the presence of wolf and goat. And these are the danger items, right? And if we do that, we can max pull or a sum or whatever, max put together, I guess. And then this f function can be a little bit easier. Because now the logical function we need to learn is only, is there not Z1 or Z2 or Z3? So is the farmer not present or is the farmer not present? And the first danger item or the second danger item happens, right? So this means by adding a little bit complexity in here, in this part, more complexity here led to lower dimension of my embeddings and less complexity in this part. Okay, so there is some kind of optimization we need to do. And unfortunately, this part is very hard in the sense of there's no clear engineering, there's no clear methodology today which tells us, just looking on data, okay, this is the kind of complexity you need here, and this is the kind of representational power you need here. This is really hard to do for the moment. On real problems, on toy problems, of course, we can do whatever we want. On real industrial problems, this is unfortunately not solved yet. So we basically try different, what is called inductive biases. So inductive bias means the structure of my network here, how items interconnect. I need to try this. And this is also a very simple graph model. So in this simple model, we have the graph items here, right, the nodes. And what in the graph I do is we first take all the different combinations of nodes and calculate this embedding here. This is what we did here, right? We take nodes and update them. So this is this operation here. We go from nodes to edges. And then we sum them all up, calculate some global thing, and then we take a decision, right? So that's a very easy model. State-of-the-art graph networks are much more complex. What they do is this kind of stuff. We go from nodes to edges, we update stuff, we go from edges back to nodes, we iterate this, we make a sum, we update some stuff, this sum goes back to the nodes. So the node here takes the full accumulation of the full graph goes back to edges, goes back to nodes. So we iteratively update lots of different things before at the end we aggregate and we decide. And there are lots of different variants how you can do that. This is used a lot in physics. Okay, in physics, when you do, for example, fluid dynamics, in fluid dynamics, all these nodes here can be particles, water particles, air particles, they interact with each other. And these interactions here can be Navier-Stokes equations or something which needs to represent Navier-Stokes equations. And you learn all this, right? So lots of people are working on this. We also work on this kind of problems. Obviously, you can do lots of things with Navier-Stokes equations directly. You can simulate them. It's not so easy. Learning can solve a couple of hard problems. So this is what graph networks are used. I give you a concrete example of how we solved this. So this is past work from my then student Fabien Paradel, and also past student of Natalia Neverova. Natalia is now with Facebook. Fabien is now with Neighbor Labs in Grenoble. And joint work with my colleague Julien and Greg Maury from Simon Fraser University in Canada. And what was the problem? The problem was activity recognition from first-person video. So you have a video camera mounted on your head, and you take a decision on the image you see, on the image sequence actually. And instead of directly putting pixels into your neural network, which is kind of possible, but also doesn't work so well, what we do is we first detect objects here. So we run an object detection that detects all of these different things. And then we model the interactions between these objects through a graph. And also a graph which finds out how these interactions change over time. And here, I will not go into details, but here you see one complex neural network, which uses all the different things we already learned in this lecture. So we have this space-time video coming in, and we have a convolutional neural network in here. This convolutional neural network will extract features, and then here we have a recurrent neural network, which takes decisions over time. So spatial decisions, convolutions over space, combined temporally over time, and we decide here what kind of activity is done. So this path alone already works. This alone can be done, okay? The second one is another path. We take these images here, and we detect objects. So we have masks, okay? These objects here will take features from this CNN here. So we collect features from the CNNs at locations detected here. And here we have a list of objects and features. We use a graph neural network, which handles interactions between objects, and have some graph network here, handle temporal instance over time, and we also take decisions. What do we gain? This part here models interactions between pixels directly. This part here handles interactions between objects, and we can also kind of explain, I'll respond to the question in the chat later. So we can here, for example, explain a little bit what kind of decisions the object takes. So we have two types of classes in this problem. We have activity classes. What is the person doing? What is it activity? What kind of activity is he doing? And the second type of class is the type of objects we see. And what you see here is the class, the activity class, person-book interaction. So this means reading, writing, whenever a person is interacting with a book. And what you see here is a co-occurrence matrix. We checked all the videos of showing this activity, and these are the co-occurrences. So there are people in their laptops, bed balls, cell phones, and a lot of times persons and books are present and all the other stuff. So this is just statistics. This is just statistics. But what we can do is we can check the decisions taken by the neural network. The neural network learned that, okay, while all these occurrences arrived for this class, only these ones are really important. So book and person, well, background is always there, okay? But person and book are the most important. Now, it sounds obvious to you that person and book interaction will lead to book and person class being important, but let's just remind you that this has been learned, right? There are only pixels going into this network. So the network learned this thing here. How did we do this? How is this graph calculated here? This graph is calculated by taking here the outputs, I'll go back to this part here. So all different comparisons of objects go into this H thing here, and this H thing outputs a vector. And we just calculated the norm of this vector, okay? So these blue bars are the norms, the accumulated norms of this vector. So this means for this person-book interaction, for example, what we can see is person and dining table is very co-occurs a lot, but the network decided that it's probably not that important. So lots of classes also completely disappeared, right? So the norms of the network are not high, meaning that the embedding which the network learned is meaningless for most of these interactions, and it concentrates on the most important one. Okay, I will switch over to transformers. I have 20 minutes because we'll have also 15 minutes of questions or so. That's okay. Now, transformers are currently the mostly highly used and mostly exciting models. So when you look at, there is most activity here. Transformers are so important that they are even applied now in areas where they are normally not, where they're not designed for. For example, we apply them for pixels. When we actually should do convolutions mathematically, when convolutions should make most sense, even there, we now use transformers. Mathematically, transformers are different. So MLPs work on every vector space models. CNNs are translation equivalent. RNNs rely on the Markov property in sequences. Suppose some graph structure. Transformers are actually models which work on sets, right? So sets, ensemble in French, sets are structures where there is basically no structure, right? There is no ordering in a set. You can change the order as you want. Funnily, we apply them now on text, which are sequences, and on images, which are grids. And I'll show you why. So they were initially proposed for learning language reasoning. So we have lots of texts where this is the first, this is the, where did this again? I want my laser pointer. So this is the famous first phrase from Anna Karenina, a Russian novel from Tolstoy. And this phrase has obviously, as the full book, been translated in lots of different languages. And what we want to do is we want to learn how to translate. And before, what people did is, when translating software was created, linguists were working together with computer scientists, mostly machine learning scientists, and linguists determined grammatical structure of languages and helped the machine learners to design models. Now linguists less and less, I'm a little bit on a limb here, I won't say not necessary, but let's say linguistic knowledge is less and less necessary. So all this grammatical structure from language, it's not that they're not necessary anymore, but all this grammatical structure and linguistic knowledge is now directly learned from large amounts of data. So we have, let's say we want to learn to translate from French to English. Well, we have millions, billions of books, they have been translated. We'll just put them into a neural network and tell the neural network, please translate that. The neural network is learned as any other neural network in a supervised way. We give it a French phrase, it's initialized randomly. We tell it, please provide the English translation. It does something. It's not working. It creates errors. We calculate the error. The correct translation is this. Minimize the error to gradient descent. There are a couple of subtleties in language, but I will not go into details. But basically, we learn neural networks on examples of translation. That's the main message I want to give. Okay. So a couple of examples. This really looks quite good. So what I did here is, this is the Catcher in the Rye in French. In French, L'Attrape-Cœur by J.D. Salinger. That's the original English. That's the Google translation. And that's the exact translation. And actually the Google translation is actually quite good. It's even better in a sense of fidelity than the official one, because in the official translation, there were some couple of artistic liberties. The Google translation is actually really, really good if you look at it. Bores me, c'est la m'ennuie. Symmetries, that's not the same language level, right? So the translator here took a couple of liberties which the automatic translation here did not do. Okay, so this works quite good. Now, how is this done? So here I need to introduce the concept of contextualization. So once more, we work on sets. So for the moment, I have a phrase: the quick brown fox jumps over the lazy dog, for example. And each word is represented by a vector. I will not go into detail how we can translate words into vectors. The most brutal thing would be a 100-dimensional vector here, where there's a single one corresponding on the dimension of the word. This is not what's done. I will not go into details. Let's just imagine I can represent each vector, each word by a vector. Okay. So contextualization means that I go from one vector space to another vector space. I translate this vector such that each representation here is contextualized by the surrounding items. So the fox here, in this vector space here, this thing here just means fox, right? In this vector space here, it's a fox, which is also brown and quick, because from understanding the sentence, the fox is quick and brown, right? But it could have been the fox jumps over the quick brown dog. Then, if it's done correctly, the fox is not contextualized with quick and brown, because quick and brown would correspond to the dog. So this contextualization process here depends on the grammar and on the rules. So anyway, this is the goal, right? This is what we want to do. The question is, how can we do that? So I'll just tell you again the mathematical structure of transformers. Obviously, these things are learned. Now, the Wolf and Farmer model will not work again anymore because it's too complicated, but I'll just give you how this thing is done. So once more, we go from one vector space, X, to another one, okay? So here we go, transformers. My input vectors here are my X's, so X1, X2, X3, etc., as before. And first of all, I have this linear transformation. V here means value. And these are my weights here, W. So the matrix of X is multiplied with the matrix of W. And obviously, this W is learned, right? So I do first a linear transformation. This linear transformation is learned. Whenever I say this is learned as before in a supervised way. So if this is my input in French, at some point I will have the output in English. And the model does a forward pass, proposes the translation, we minimize, we derive, and minimize the difference. Okay, so this is learned. Good. Now, learning is, for the moment, this is independent, right? Because I take each data item here and I project it into some space. So this is linear transformation. And for the moment, this is independent of the other vector. So this is not what I want. At some point, I want to use this thing here and make it be influenced by the other guys. The problem is, these other guys, there are lots of them. And as I said before, in the case of the brown fox, I would like to make this thing be influenced by quick and brown. So these two guys here should just spill over here. But if my phrase is the fox jumps over the quick brown dog, then quick and brown should not go in here, right? So basically what we want is we want to have some influence here by the other guys, but this influence should be learned. So this is called an attention model. And what we'll do is each item here will put attention on a couple of the other items. How is this done? Well, we learn two other projections. So we now have three of them. This is value, okay? It's the value one. And this thing is called query, and this is the key. So there are three different linear projections. The one we already saw, and the two other ones are two other matrices. So the query vector and the query matrix and the key matrix. And what does this mean is these two guys here, so the beige and the orange one, are two linear projections of the input, which will define a space in which we calculate similarities. Okay, so basically I'm going back 1 second. Okay, Fox here. Would like to check where should we look at. We should know that quick and brown here is important. Quick and brown needs to have an influence on Fox. So to do that, we calculate the similarity between the vectors. The problem is we can't look at the vectors themselves because Fox is not similar to brown. Fox is not quick, similar to quick. And also, if I just calculate similarities on my input space, then this similarity does not depend on the position of quick and brown. Once more, if quick and brown is here, then it should influence Fox. If quick and brown is after, it should not, right? So I cannot calculate my similarity on the input space. So what do? Is I calculate in a new space, in a space spanned by query and key. So these are two vector spaces, okay? So why do I need two different vector spaces? Because my similarity function will be leading to a similarity distribution and attention distribution, which is different for each vector. So my first vector here, my first item will be enriched, and I'll need to check whether I look here and here and here and here and here, right? So I need a similarity distribution, something like here. So apparently this model looks a lot here, a little bit less here, and not much here, right? So this is only the distribution for this vector here. So this vector here, to enrich this value here, I have one distribution. I will have a second distribution for this one. For this one, I have this distribution. How do I do that? Well, I take this query and key projections here, and I calculate the similarity between these two by just projecting them to each other. I just do a dot product similarity between these two. And what I do then is I normalize this over the keys. So I'll go back slowly. What does this mean? For this here, I take the query, my query, the query for this guy here. I'll take all the keys of the other one, and I calculate the similarity between my query and this key, my query and this key, my query and this key, my query and this key. I normalize them, and I got some kind of probability distribution. Okay. Second part here, I'll take my query and the similarity between this key, this key, this key. So this is the reason why we have keys and queries. Queries are vector spaces, embeddings, which tell each item, what am I looking for? What am I looking for? What is important for me? What is important for the Fox, for example? The Fox needs to check the adjectives which correspond to him, right? Whereas the keys here are not the things which I'm looking for, the things which I respond to. So the key is when somebody looks at me and wants me to respond, I'll respond with my key vector. And these three matrices are learned, okay? So how do we continue? As I said, we have as many probability distributions as we have input items. And for each item then, we take all these values here. Let's not forget the green ones. The values here I actually summed up. There's a huge sum here. And the sum is weighted by my attention, right? So second one here. So each input vector is transformed first into a value, and then again into a weighted sum of all the values, and the weights here are determined by my similarity. So these models here can also be stacked, and they can be multi-headed. Let's go back to my explanation here, translating this French into English. Well, we have our inputs here, multi-head attention. What does this mean, multi-head? Multi-head means that whenever I calculate query key value, there is not one of these query key value attention models, there are multiples of them. At each layer, I have typically 8, 16 of them, okay? So this means that when my Fox here enriches, goes from this vector space to this here, it will look at quick and brown, will also look to others. So each head, each attention distribution will have a different role. And actually, there are people in Oxford Lena Voita, a PhD student in Oxford, looked at these multi-head attention distributions and cross-checked them with grammar and syntax. So she calculated lots of indicators of grammatical relationships in text and found out that the different heads of attention distributions actually correspond to different grammatical functions. I will speed up a little bit because I want to show you a large-scale reasoning application. I will a little bit spill over in the next session. That's okay. I will not speed up. I'll just spill over 10 minutes in the second session. That's okay. So let's integrate all this and let's have a look at a large-scale application. So this is a project I'm working on with multiple PhD, well, 2 PhD students actually, but it's obviously something which is done by the whole field, which is called vision and language reasoning, or in particular application is visual question answering. So we have pairs of images and questions here, and the model needs to answer, it needs to look at the question, needs to understand the question, look at the image, and then answer the question. And some of these questions are easy to understand. So how much money do I have in my hand? You just look at the bill here and say 10 euros. What is in this jar here? Well, you need to find the correct jar already from all these jars and read the text and say coffee. They're quite easy to do, but obviously they depend on the text. Okay, but there can also be a little bit more complex. Did I leave the door open? You need to find out what is the state of my door here. Did I leave the lights on? Well, apparently they seem to be on. Can you imagine what kind of application I could use this for? So what kind of industrial, really nice application could use this kind of software? Nobody? Sit down a little bit. Sorry. Nobody, anybody? Any industrial application where you can answer arbitrary questions on images? No? Okay. Help for the visually impaired, blind, for example. You could imagine you're wearing some kind of Google Glass-like glasses. You have a first-person camera on you, and the camera sees everything you see, and you can leave the house and ask this kind of questions here. How much money do I have in my hand? You don't see yourself, the bill, but the camera sees the image, recognizes speech, provides text to neural network answers you, speech to text, text to speech will synthesize the output. You're holding a $10 bill, a 10 euro bill, etc., etc. So this is really one of the projects we're working on together with Orange company. So this is one of the state-of-the-art models, UMLP 2019, so it's 2 years old, but really widely used, and it uses transformers. So the same transformers so this kind of models here, transformers, are used in the same kind of application, and they're a little bit different because they need to work on images and text. So how does this work? The text here comes in, a woman riding a bike with a dog in a basket, and you calculate all, you translate, you take each word, you calculate a vector. I will not explain how this works, but you translate each word into a vector. Then you use some kind of object detection software to detect objects. So you have a set of object items. Each object is also described by a vector, which corresponds to its visual experience. And then you have a transformer. One transformer here and one transformer here. They're separate. The transformer here will check all the different visual objects and combine them together and contextualize the different objects here. The language transformer here will check all the different words and contextualize them as we did before, right? So this is a language, it's called a language encoder, and this is called an object relationship encoder. It's also called self-attention. Self-attention because the modality attends to itself. Text attends to itself, object attends to itself. And then we have layers of what is called cross-attention. Cross-attention means that objects look at text, right? What would that mean in my transformer here? That would mean that actually I have sets of images and sets of text. My value comes from the text, but my query and my key comes from the objects, or the other way around. my query and key could come from text items, my value comes from objects. So this means that we learn how these different objects here are related to the text here, right? And at the end, everything is transformed. Transformers, the name comes from the fact that you input vectors and they are transformed over time. And at the end, you have a set of transformed outputs. Now, what we need is a decision. So what do we do? Well, the yellow stuff in here is a dummy word. It's called class. This dummy word doesn't correspond to any word. This dummy word is transformed with all the other ones and outputs here the answer. So the transformer learns how to take a non-existent word, transform it over time. Well, time is meaning iterations in the model. Contextualize this non-existent word with the other words, calculate where do I need to look in my image, transform it, and then provide an output. Okay. So I'll stop here. I have a couple of more slides, and I think I will present the slides after the break. Well, we have break in 15 minutes, but I think 15 minutes might be interesting to for questions. So if you have questions, I'd be happy to take them now, and I'll continue afterwards with the application. I'll try to open my chat a little bit more. Better see. Are there open questions which have been asked before in the chat or not? The second line of matrix U, yes, you're right. Thinking about it in my head, you're completely right. I think that's a copy-paste error, yes. So that's an excellent question. How does the model learn that brown applies to fox and not the dog? So what we, how can I go back here? So the question is, how does the model learn that fox applies to, no, that brown applies to the fox and not the dog? Don't forget that it's a stacked model. So I didn't really talk about this a lot, but basically what you can have is you have, okay, I'll take the long road, sorry. So this is the model for translation here, right? So we have here an input embedding, inputs, and we have one transformer. The transformer is followed by an MLP. Feed forward basically means an MLP, a multi-layer perceptron. Then it goes into another transformer, and these are the preceding outputs. So basically the inputs go in, and it will take one word per transformer. So what I do here, I give it the previous words which already have been translated. It performs transformer attention over this, combines it with the new input, and takes the output. So that's not really important. What's important is that you have multiple layers, one layer, two layers, right? So one attention operation here, and already even in one layer, you have multiple heads, right? Multiple heads means that multiple triplets query key values, okay? So this means that, going back to your question, what you could do is, if you have the quick brown fox, for example, the first layer of attention somehow tries to understand grammar, so finds out that there's a jumps afterwards, right? Jumps is here. The quick brown jumps found that the presence of jumps and the position of jumps with quick and brown means that this thing here is a subject, right? And this is the verb here, and the object is after. So the first layer could find out from sequential information syntactic structure, and the second layer could use this to then say, okay, now I know where to look for. I'll look, a fox will need to be here because they are both joined. They're called in French a nominal group or something, right? So they're in the same nominal group, and attention needs to attend to them, right? So over multiple layers, you can do that. Nobody asked another question, which I was hoping for. No, somebody should have said, sir, this doesn't work. I omitted crucial information. I told you that we know that this guy is in the input example, Degrid Crown Fox jumps. We know that this information here, the fact that this is a nominal group, stems from the information that they are joined together in a single space and that the verb follows them, right? But that's not something the model can know. Why not? If we do it, if we apply it naively, the model cannot know that because the model applies on sets and not sequences. Remember, when I started to talk, I told you that permutation equivariance. Permutation equivariance means you permutate your set, you change the order. The model does not notice anything. It's equivalent to permutations. It's not a sequence like in RNNs, it's a set, right? So this is easily seen by the fact that this distribution here just takes these protections here and not the positions. So the positions here is never used, right? We never use positions. This is the reason why when we apply these models to sequences, we apply positional encodings here. So since these models apply to sets and not sequences, we do positional encodings. What does this mean? Part of this vector here corresponds to the word, and part of it is the position in the text. The easiest thing would be to add one more dimension, say 1, 2, 3, 4, 5, 6. Okay. In reality, what we do, we calculate some kind of Fourier transform kind of position encoding. So we have sine and cosine waves of different frequencies. In any way, it's not important. This is the reason why I have this sine wave here. Position needs to be encoded into the input because the model else would not understand what positions are. Okay. Any other questions? HMMs and RNNs. That's an excellent question. There is a huge difference because in RNNs, so basically, do I have any? I have slides for that, but I don't want to search them because it will take ages to connect my computer. But basically, in an RNN, you do a forward pass, right? You go. I don't have the perfect slides for that. In an RNN, you do a forward pass over your model, and there is no optimization during inference, right? So, excellent question. I'll come back to this later, how the initialization RNN. But let's just imagine my H0, which we don't do, but let's just imagine it's somehow initialized, okay? So what you do in an RNN, you have a forward pass. During, you have the training phase and you have the test phase, right? Test phase means you deploy your model, it works in real life. In the test phase, you go with a forward pass through your model and no decision is ever questioned. It's completely deterministic. It's a DAG, it's a directed acyclic graph. You calculate the output is done. There is no optimization. Optimization is done during training. During training, you do a stochastic gradient descent, right? And you optimize the parameters, but once they're done, the calculation is a DAG. Whereas in HMMs, you perform optimization both in training and in testing, right? Because during training, you use something like the Baum-Welsh algorithm to find your matrices. You have something similar to these matrices here. They're not completely equal. Your state, most HMMs here have discrete state. There are also continuous states, but most of them are discrete. So your matrices are basically state transition matrices, right? And you learn these matrices and a couple of other ones, observation matrices, but also during observation, during deployment, you also need to learn, you need to optimize something, right? Because you solve, for example, the Viterbi algorithm, you fit, you optimize, you calculate the optimal state sequence for your observation. So they're really quite different. I need to talk 15 more minutes on the difference, but graphical models are not working like neural networks. Yes?
No, thank you, Christian.
Okay.
Thank you.
How to initialize H in RNN? Multiple possibilities. Either it's always a fixed value, it can even be 0, or you can learn the initial value as a parameter. That's open to you. So you can take H0 and make it trainable. So it's a trainable value, can be. Any other questions?
Yes, related to initialization. It is sensitive to yes, to initialization. In fact, to optimize the network, there is like you know, it's like in expectation maximization. It can be sensitive. In fact, to optimize, and there is for RNN the same problem, the same issue.
Yes, totally. I'm not an expert in this either, but I'm not sure there is really lots of research in this area, but there are a couple of standard procedures, Xavier initialization, Hay initialization. Obviously, if you do some stupid things, and stupid things might be, for example, initialize everything to 0 or to the same values, since you don't have any noise in your update process, gradient descent will just blindly not work at all, because everything goes to the same direction. So basically, you do it stochastically, and you use some form of random models, Gaussian distributions, and then mostly you use some form of white noise to have different frequencies into. I honestly don't know the details anymore of these processes, but basically mostly use Xavier and Hay initialization, which are these kind of operations. I don't know the details anymore. But okay. Yes, it's second answer is, first one is, what do you do? Second answer is it sensitive to it? Yes. So this is one of the big problems we have in experimental machine learning right now. Is obviously it's sensitive even to the seeds, right? And very often seeds are fixed during training. And one of the things you really need to do is, if you want to really be serious, and obviously you should be serious about that, is to test lots of different seeds and calculate the standard deviation of your evaluation metrics on multiple seeds, 3 at least, or 5. And depending on the model, you can have quite big differences, and depends on the numerical stability, and that depends on your network actually. So I'll give one example. ResNets actually, ResNets, for those who don't know, residual networks were the type of networks which solved a couple of numerical problems in deep learning. So before 2015, before ResNets arrived, we were able to learn models up to a certain depth. If depth, so depth means number of layers. If we increase the number of layers, then if training doesn't go well, validation performance, so generalization performance to unseen data goes down. But actually, at some point, even training performance went down. So we trained models up to, let's say, 20, 25 layers. And then you had a good performance, and then you added another layer, and training performance went down. And that's funny, because that means you have a numerical optimization problem, because obviously adding one more layer means that your model will be at least as expressive, right? So you should get the same solution, but we didn't. So what ResNets did is they decomposed instead that each function, each layer learns to transform another layer. It learns the residual. So it learns what do I need to add to the last layer to change it. And this changed the complexity of each individual layer, made the geometric transformation easier and easier to learn, and solved numerical problems. So why do I say that in this context? Depending on the numerical stability of your model, on the different conditioning, etc., you can have more or less dependence on your initial values. This is the reason why we also, for example, in some critical applications where, for example, process control, automatique, etc., we want the models to be robust. We apply constraints, for example, Lipschitz constants. You can, for example, constrain a network such that the Lipschitz constant is fixed and limited and bounded. I'm going away from the initial question. Are there other questions? Okay. If I understood correctly, there are 15 minutes break. So what follows is one more. So this was an introduction. now I will go a little bit more into a very specific application afterwards, visual question answering. This will take, I think, 10 minutes, perhaps 15 max. And then I will give you a live coding session, how this is actually coded in PyTorch. But a very simple example, okay? A very, very easy example. So see you in 15 minutes.